In this problem, we're assigned the task of finding I1, I2, I3, and I4. You can see those currents labeled on the diagram. Again, we use our problem-solving strategy for op-amp circuits. And if you remember, one of the assumptions is that these two currents are zero. So this tells us, for instance, that I1 is equal to 0. And if you'll also remember, the voltage across these two terminals here, between these two terminals, is 0. So if I define this voltage as V1, then the voltage at this node with respect to ground is also 0. Now let's look at Kirchhoff's current law. At this node, we have 1 milliamp entering. This node, we know there's 0 going into the op-amp. So this tells us that this current is 1 milliamp. And then the voltage across this resistor is 5 volts. So if we look at our circuit then, it tells us that V1 is equal to 5 volts. And so now, also if we look, if we define this current as Ix, then from Ohm's law, we can get that Ix is V1 over 10K, which is 5 over 10K, or 0.5 milliamps. And now, if we apply Kirchhoff's current law at this node, for instance, we'll have a current of Ix leaving and a current of I3 leaving, and by Kirchhoff's current law, those have to be summed to 0. So I3 is a negative of Ix, so then I3 is minus 0.5 milliamps. And if we look then, the current flow in this direction is 0.5 milliamps. Then the voltage across this resistor with this polarity is 2.5 volts. Now let's define a voltage V4 across the 10K resistor. And if we apply Kirchhoff's voltage law around this loop, we'll get V4 is equal to 2.5 plus 5, or 7.5 volts. So then, I4 then is 7.5 divided by 10K, 0.75 milliamps. And then to find I2, so now we have I1, and we have I3, we have I4, so now we need to find I2, and we can apply Kirchhoff's current law to that one node. So now this current is 0. So if we apply Kirchhoff's current law to that node, we'll have I2 entering, we'll have 0.5 milliamps leaving through this path, and this path will have 0.75 milliamps. So then that'll give us 1.25 milliamps for I2.